Welcome back, Chemi 330 students. Before we begin this next example, I just wanted to make a note that there was a sign error in the first video. The video description has been updated to include that, and any future corrections will also be added to video descriptions, so keep an eye out for those as you're solving these problems. Example 2 is a problem dealing with viscosity. In this problem, we have an oil serving as lubricant between a shaft and a sleeve, and our goal is to calculate the power loss in the bearing for a sleeve of known length. Now you should pause the video and try to solve this on your own before we work through the solution. So we have a shaft in the center of a sleeve with oil serving as lubricant in the open space between the two. From the problem statement, we know that the sleeve is 90 millimeters long, the shaft is 0.4 meters in diameter, and the distance between the sleeve and the shaft is 1.5 millimeters. Now that we can picture the setup, let's list all of the given information together. Our viscosity is 6 poise, and we can convert that to SI units, giving us a value of 0.6 Newton seconds per square meter. As shown in our drawing, our shaft diameter is 0.4 meters. Our number of revolutions per minute is 190. Our sleeve length is 90 millimeters, or 90 times 10 to the negative third meters. The oil thickness between the shaft and the sleeve is 1.5 millimeters, or 1.5 times 10 to the negative third meters. The first step in calculating our lost power is going to be calculating the tangential velocity of the shaft. This is equal to the circumference of the shaft times the rotational speed divided by a factor of 60 to convert the minutes in RPM to seconds. So we substitute in our known values, and the result is a tangential velocity of 3.98 meters per second. We'll add that value to our given information on the right and move on to calculating shear stress on the shaft. The formula for shear stress is our viscosity, mu, times its derivative du dy. Du represents the change of velocity, and dy represents the change of distance. We can calculate du as the difference between the tangential velocity of the shaft and that at the sleeve, which of course is 0. So du is simply equal to u in this case, which is 3.98 meters per second. Our corresponding change in distance for that change in velocity is then just the distance between the shaft and the sleeve, which is simply t. And we know that the value of t is 1.5 times 10 to the negative third meters. So substituting these values into our equation for shear stress, we get a value of 1592 newtons per square meter. From that value of shear stress, we then want to calculate the shear force on the shaft. Shear force is the shear stress multiplied by the area over which it acts. In this case, that's the surface area of the shaft that's enclosed by the sleeve, which is given by the circumference of the shaft multiplied by the sleeve length. So this is the final form of our equation for shear force. We substitute our known values, and evaluating gives a shear force of 180 newtons. The last step before calculating our lost power is to find the torque on the shaft using the shear force that we just calculated. Torque is given by force multiplied by half of the shaft diameter, as that is the length that essentially acts as our lever arm in this problem. Again, we substitute our known values, and the result is a torque of 36 Newton meters. So finally, we're ready to calculate the power lost. The equation for power is 2 pi nt, again divided by a factor of 60 to convert that minutes in RPM to seconds. We substitute and solve, and get a value of 716 watts, which is the final answer for this problem. This example is from a textbook of fluid mechanics and hydraulic machines. Again, I would recommend that you solve this a few times until you're comfortable with the material.